Okay, hello everyone. I am Gokul Vasudevan. I'm a PhD candidate here in the School of Civil Engineering at Oregon State University. And this research was performed with the guidance of my advisor, David Trejo. And today I'm going to be talking about standardizing corrosion assessment methods for alternate cementitious systems. All right, so here's the outline. So first, I'll be starting with an introduction, followed by the research challenges involved and highlighting the need for research in this area. And then I'll be talking about the test method. We are actually proposing a new test method for corrosion assessment of ACM systems, and I'll be giving you some details on that. Then onto the experimental program that was implemented for the study. And select preliminary results will also be shown from my experimental program. And finally, a short summary highlighting the important takeaway points and the future of this method. Okay, so at this point, we know that use of alternate cementitious systems, also just commonly known as ACMs, can reduce the energy and carbon footprint associated with concrete. And as the previous speakers mentioned, ACMs are a good fit for specialty applications. However, at the same time, it needs to be ensured that the inclusion of these materials do not compromise the strength and durability offered by the traditional OPC systems. So this is fairly important because using a new cement just because it has a lower embodied carbon may not be a wise decision in the long run. So we need to absolutely make sure that the long-term performance and durability of the systems is comparable to that of Portland cement systems. So there is a need to establish whether standardized test methods that are used to study the durability of traditional OPC systems are also valid for the ACM systems or not. Okay. And talking about durability, in my study, we are going to be focusing on the corrosion side of things because it has vastly been reported that corrosion is responsible for more than 90% of the durability issues plaguing concrete. So my research focuses on corrosion. So talking about corrosion, a challenge in this regard when it comes to corrosion is to establish a chloride-induced corrosion testing method that are also valid for ACMs. And doing chloride-induced corrosion testing typically involves measuring the critical chloride concentration, critical chloride threshold, also known as CL crit here. So CL crit is the amount of chlorides necessary to result in active corrosion of steel reinforcement embedded in the cementitious materials. So when the amount of chloride in the steel concrete interface exceeds the CL crit, we have initiation of corrosion. So engineers working on concrete design have to keep this in mind to ensure that the critical threshold value of chloride is not breached. And the CL crit is a prominent parameter because it is used to estimate the service life of reinforced concrete structures. Okay. And CL crit, as I mentioned earlier, is a very prominent parameter. And in spite of all that, it is surprising that there is very little agreement in the industry on the CL crit values. And recent studies have shown that the new OC crit test method can yield results faster and much more reliably when compared to other accelerated corrosion tests. So the thing with this OC crit method, though, is that it has currently only been standardized for mortar or concrete made with OPC systems. So in order to make it a much more complete and a much more comprehensive method, we should standardize the test so that it is applicable for all cementitious systems. Okay. Yeah. And here are the references for the first few works that was carried out on the OC crit testing methods. All right. So moving on to the test method. So here's what the test setup looks like. So this big rectangular block that you see here is the cathodic specimen, and there are 5 reinforcement bars embedded inside this cathodic specimen, and the cathode actually goes in a tub with saturated calcium hydroxide solution. And you can see here that the cathode, the 5 reinforcement bars embedded inside the cathodes are connected to 5 anodic specimens, and you can see that there is an electrical connection here, and there is also a salt bridge to ensure that there is an ionic connection so that all the ions can transfer back and forth between the anodic and the cathodic solutions. So that's the test setup. And so what we do here is we consider that corrosion has initiated when the open circuit potential is more negative than negative 350 millivolt for 2 consecutive days. So this criteria of negative 350 millivolt is with respect to copper sulfate electrodes. However, other standard electrodes can also be used, and the threshold criteria has to be adjusted accordingly though. So once the activation criteria is reached, the critical chloride threshold values, the CL crit values, are determined by extracting the sample from the mortar cover. Okay. So since the OC crit test method is fairly new to everyone, and since only a very select group of universities are working on this method right now, let me just give you a little bit of rundown on how this method works. So the first step, as I just mentioned briefly earlier, is to monitor the open circuit potential. So the open circuit potential of the specimens are monitored until the activation criteria is reached, and the activation criteria is negative 350 millivolt with respect to copper sulfate electrode. And the second point is, so once the activation criteria is reached, we do chloride analysis. So mortar cover is extracted and investigated for chlorides to determine the average chloride concentration, which I'm calling at this point as CL test. So at this point, I have to kind of pause and make an important clarification, because measuring the chlorides in the mortar cover only tells me the average chloride concentration of the cover. This should not be misinterpreted as the critical chloride concentration CL crit, because CL crit by definition is the concentration of the chlorides at the steel mortar interface. So we actually have a couple more steps in order to find what our CL crit is. So that is what we do here. So we try to establish a link between the CL crit, which is what we need at the end of the day, and the CL test values, which we get from this method. So what we do here is we cast some partner specimens to generate data to establish a relationship between CL crit and CL test. So cylindrical specimens like this are cast, and they are exposed to different chloride solutions for different durations, and then we grind the layers down layer by layer, and then we test them for chlorides to establish a relationship between CL crit and CL test. And then once we have the data from these specimens, we can actually do some statistical analysis. And I have used a multiple linear regression technique in order to come up with a relationship between the CL crit and the CL test values. And here's the experimental program that we looked into. So we had 3 different types of cements: OPC, CAC, and CSA, and also 3 different water cement ratios: 0.35, 45, and 55. And when it comes to CSA, 2 curing conditions were investigated. The first curing condition was wet curing, which was done in a typical mist room at 100% relative humidity. And the second method of curing was ambient cure. This was done in standard laboratory conditions and not in a mist room. And this was done at a temperature of around 23 degrees Celsius with a rough relative humidity of around 50%. And when coming to CAC, again, we investigated 2 cases, which is the converted scenario and also the non-converted scenario. And the experimental program is summed up in this table here. And then for each case, so we looked at a full factorial design. But again, these factors are only applicable to CSA and these factors are only applicable to CAC. But other than that, it is a full factorial design. And for each case, we looked at 5 anodic specimens and 1 cathodic specimen. Okay, so now I'm going to be moving on to the results. Okay, so these are the results from monitoring the open circuit potential. So again, I'm presenting the results here from only one scenario in the interest of time. So I'm only showing the results from the specimens which had a water to cement ratio of 0.35. So let me just walk you through the first plot here. So on the x-axis, I have the exposure time in days. And then on the y-axis, I have the open circuit potential with respect to copper sulfate electrode. And this was done on OPC specimens with a water to cement ratio of 0.35, and they were exposed to a chloride solution of 2%. So you can see here that the anodic specimens here have an average time to activation of around 40.8 days. You can see here that roughly around the 40-day mark, almost all the specimens have reached a voltage which is more negative than negative 350 millivolt for at least 2 consecutive days. So the activation time is around 40.8 days here. And moving on to the CSA specimens, we can see here that again, I have 2 cases here, the WC that indicates wet cure and AC here indicates ambient cure. So you can see here that the specimens that were wet cure has a mean time to activation of around 8.8 days. And then the same number in case of ambient cured specimens comes out to around 7.6 days. And moving on to CAC specimens. So here, this is the non-converted specimen, and here I have the converted specimens. So we can see here that the time to activation for the CAC non-converted specimens is around 74.2 days. And the same number for the CAC converted specimen comes out to around 69 days. And another distinction that you can see here is when it comes to OPC specimens, we used a chloride solution of 2%, and here we are only using a chloride solution of 1%. That is because at the start of the program, we were a little apprehensive about the chloride concentrations, using very high chloride concentrations for CSA and CAC because we were not exactly sure how they were going to behave. So we went with actually a lower concentration of 1% for CSA and CAC cements in order to completely capture their behavior. And then moving on, so here are the results from the CL test, which is the average chloride concentration. And again, I would like to point out here that this values only indicate the average chloride concentration of the cover, which I'm calling CL test. And this is not to be misinterpreted as CL crit, which is the actual critical chloride concentration. So here, again, I'm showing 3 plots here, one for OPC, one for CSA, and one for CAC. And you can see here that the CL test values for the OPC specimens actually range anywhere between 0.3 to almost 0.6 here. And then for CSA, you can see that it's slightly lower. The values are ranging anywhere between 0.1 to 0.3. And then when it comes to CAC, you can see that the values are slightly higher, especially at higher water cement ratios, like at 0.45 non-converted and 0.45 converted. We can see here that the CL test values are roughly between 0.5 to 1%. And then we can observe the same thing for 0.55 water cement ratio as well for both non-converted and converted CAC specimens. Again, the reason that I'm presenting the CL test results here is it is just an intermediate step towards determining the CL crit values. So the key idea here is to simplify the test. So because determining the CL crit values by extracting the samples from the interface could be quite a challenging task. So it will be convenient to measure the CL test values like I'm showing here, and then using the CL test values to determine the final CL crit values based on some statistical methods. All right, so finally, I'm coming to the CL crit values here, which is the critical crit concentration. And as I just mentioned earlier, the CL crit values that I'm showing here is calculated from the CL test values, which I showed in the previous slide using the developed statistical models. And again, I have three plots here, one for OPC, one for CSA, and one for CAC. And you can see here that the critical crit concentration of OPC specimens across all water cement ratios are ranging anywhere between 0.2 to 0.4. And then for CSA, you can see here that almost for all the cases, like whether it's wet cured or ambient cured, and also across different water to cement ratios, we can see here that the critical crit values, just percentage by weight of cement, is ranging between 0.1 to almost 0.3. And again, when it comes to CAC, we can see here that especially at higher water to cement ratios, like 0.45 and 0.55, the critical crit concentrations are between 0.4 to 0.8. So that's the takeaway from this is the CAC systems exhibit a higher CL crit value when compared to OPC and CSA systems. And OPC and CSA systems show comparable CL crit values. And then moving on to a quick summary. So we have shown here that the OC crit method can be used to determine the CL crit values of OPC and ACM systems in a fast and reliable manner. And additionally, the results procured from the OC crit method can also be used to predict the service life of structures. So I briefly spoke about generating data to develop models that can be used to determine CL crit from the CL test values. The data from the specimens can also be used to determine the diffusion coefficient of the mortar cover. And then when you have the diffusion coefficient values and also the CL crit values, it is convenient to plug those values in and use those values to determine the time to corrosion initiation. And again, this method is still under work, and the ACI 222 task group 1 is currently working on standardizing this test method. Okay. Yeah, thank you for listening.